Hi, my name is Nicholas Mathias, and today we'll be talking about integration with respect to measure. This covers largely section 3a and then goes into chapter 5. We will first begin Lebesgue measure on R. We'll be using a lot of the key definitions from Axler's book to get a geometric understanding of what Lebesgue measure is, and then we'll be using it to interpret the money analogy posed in one of the homework problems. From there, we'll expand Lebesgue integration to R2 and try to maintain the intuition throughout the entire presentation. The first definition that we have of an integral in a measure space is definition 3.3, which deals only with non-negative functions. So we suppose that x s mu is a measure space, and that f is an s-measurable function mapping our measure space to non-negative real values. The integral of f with respect to the measure, denoted the integral of f d mu, is defined by the supremum of the lower Lebesgue sums, where P is an S partition of X. This definition is important in a lot of Axler's later results. However, it's not the best for building intuition right off the bat, so we'll begin geometrically. Here we have a coordinate axis. On the horizontal axis, we have our measure space X, which is of course coupled with our sigma algebra S and our measure mu. On the vertical axis, we have a set of real numbers, and thus we can draw a function f. We don't yet have the tools to build intuition for what Lebesgue measure is. However, we'll be coming back to this graph when we set up a little bit more to work with. One of the most important things to note moving forward is that in definition 3.3, we actually allow f to take on values of infinity. This is one of the biggest advantages of Lebesgue integration over Riemann integration. However, to keep things intuitive, I have assumed that f is bounded here so that we can more easily picture what's going on. We first move to definition 3.4, the integral of a characteristic function, as the first step in building intuition for what the Lebesgue integral looks like geometrically. We first suppose that x s mu is a measure space, and that E is an element of the sigma algebra S. We then claim that the integral of the characteristic function on E d mu is the measure of E itself. This definition is one of the simplest ones we'll be going over today, and is among the easiest to swallow. However, that won't stop us from going ahead and looking at a graph to see how we arrive at this definition. pictured below is a familiar blue axis. However, we're not yet ready to consider the graph f. Instead, I've marked some sets from the S partition S, which will prove useful in our visualization of the integral of the characteristic function of E. We don't yet care about S partitions or even multiple sets from the sigma algebra S. Instead, we pick out a single set E from our sigma algebra. We will be finding the integral of the characteristic function on E with respect to the measure mu. Remember that the characteristic function takes on a value of 1 when our input, x, is in E, and a function value of 0 when our input x is outside of E. Thus, we have the characteristic function pictured here. To find the integral, it's consistent with what we see in Riemann integration. We are looking for the area of these boxes. The height of these boxes will always be 1. Thus, the area is just the length. This is where we arrive at our measure of E, because what we care about is the length of the interval E for the area under the curve. Our first step to handling more complicated functions, like the function f we drew at the beginning of the presentation, is definition 3.7, the integral of a simple function. Recall that simple functions are functions that take on only a finite number of values in the range. We suppose that x s mu is a measure space, and that E1, E2 through En are disjoint sets from our sigma algebra. Moreover, we fix C1, C2 all the way through Cn, such that they are non-negative real numbers. Note, once again, that C can take on the value of infinity. We'll be working with finite values of C for intuition purposes. Moreover, we're still operating under the assumption that these function values are non-negative. We will talk about how to handle functions with negative values at the end of the presentation. For now, we describe the integral with respect to measure as the sum of these simple functions, which becomes the sum of the function values times the measure of the set that reaches said function value. Once again, we will turn to geometry to make sure we understand what's going on. We turn to our familiar blue axis. Pictured below are four sets from the sigma algebra S: E1, E2, E3, and E4. Before, we cared only about the characteristic function on any one of these sets. However, we are now working with a simple function, which can take on values that are not 1. This is where our scaling factors C come in. For the set E1, the simple function reaches the value C1. So we scale the characteristic function by C1. The same is true for C2, and for C3, note that we do not have the requirement that C1, C2, and so on are strictly increasing. So C3 can be all the way down here. Lastly, our simple function reaches the value of C4 on this interval here. If we wanted to find the integral of any one of these sets E, we would have a case similar to definition 3.4. However, this time we're not just dealing with the characteristic function. We're scaling the characteristic function by our scaling factors C. Thus, we can think of the integral as being in parts. The integral of the set E1 is still the measure of E1, but the height of these boxes is now C1. That's not our entire function anymore, though, so we need to do the same for the rest. For C2, we have the box as the measure of E2 times C2. Here we have the measure of E3 times the height of C3, and lastly, the measure of E4 times the height C4. If we add these all together, we get the area underneath the curve, and this is where our above formula comes from. Result 3.9 is one of the most important results in the section when it comes to our discussion here. It's what ties our discussion about simple functions and characteristic functions to the graph that we drew at the beginning of the presentation, F. So, result 3.9, integrals via simple functions, says that we suppose that x S mu is a measure space, and that F maps this measure space into non-negative real numbers. Not only that, F is also S-measurable. This is one of the most complicated looking results in the entire section. We defined the integral F with respect to measure by first fixing A1 through AM, which are disjoint sets in the sigma algebra, and finding C1 through Cm such that they are non-negative real values, and that f of x is greater than the simple function defined by these scaling factors. then the integral is the supremum of all possible disjoint sets in S, A1 through AM, such that we've taken the integral of the simple function on each one of these A1 through AM. This definition alone was the entire reason I wanted to make this presentation, and I can't wait to show you how easy it really is. Pictured here are A1, A2, and A3, three sets from the sigma algebra S on X. We're finally ready to talk about the initial function we teased at the beginning of the presentation. We need to pick out values of C1, C2, and C3 such that f is above these values on the entirety of each interval. C1 is here, C2 is here, and C3 is here. It's a bit unclear from the picture whether or not C2 and C3 are exactly equal, so I took some liberties on the vertical axis. We can see pretty clearly that the integral doesn't do a good job. From our previous result, if we take the integral of this simple function, then we can see that the area under the curve doesn't even come close to the area under f. So in order to get a better approximation, we're going to need to refine our sets just a little bit more. Here, I've done just that. I've picked out A1 through A6. Notice that we're still talking about the same region. The union of A1 through A6 is the exact same as the previous A1 through A3. However, because our intervals are smaller, we can be a little bit more precise with our choice of C1 through C6. I picked C1 here, C2 here, C3, C4, C5, and C6. Taking the integral we can see a noticeable improvement over the last slide. Of course, we're still not doing a great job. We would need to refine further in order to reach that tall portion of graph f there. However, we can see that continuing in this fashion would give us a better and better approximation of the area underneath the curve. This is why our integral is defined as the supremum of all the integrals of these simple functions that we use to approximate f. Result 315 is nearly identical to previous result 3.9, but this time we're dealing with the integral of a linear combination of characteristic functions. We suppose x s mu is a measure space, and E1, E2 through En are sets in our sigma algebra S. Furthermore, we fix C1, C2 through Cn to be some non-negative real numbers. In this case, Haxler states that the integral of the summation of these characteristic functions scaled by ck is, in fact, still the summation of the measure of the set in question multiplied by the output value for the simple function. The intuition here doesn't change much from what we've discussed in the past, so I think we're finally ready to move on to the money analogy. Here, Lebesgue uses an analogy to highlight the difference between his method of integration and Riemann integration. He says that I have to pay a certain sum, which I have collected in my pocket. I take the bills and coins out of my pocket and give them to the creditor in the order I find them until I reach a total sum. This is the Riemann integral, but I can proceed differently. After I take all the money out of my pocket, I order the bills and coins according to identical values, and then I pay the several heaps, one after the other, to the creditor. That is my integral. Because I assumed f was bounded from the very beginning, we can think of the area under the curve of f as the finite value which we are trying to pay. First, we'll use Riemann integration. We fix a series of intervals and we use boxes to approximate the graph as we move from left to right along the axis. And we do in fact get an approximation for the area underneath the curve. Lebesgue proceeds differently, however. While Riemann partitions the domain into a series of intervals, then uses the output to approximate the height of the box, Lebesgue picks out simple functions that approximate our graph f during certain intervals. Once we've got all our simple functions drawn, we can proceed to integrate on each one to get the same area underneath the curve. However, instead of starting in the domain and using the output of f to get an idea of the height of our boxes, we started with the height and then we measured the length of the given boxes. And that is why Lebesgue integration can be thought of as partitioning the range as opposed to the domain. Of course, restricting our available functions to functions that are exclusively non-negative almost outweighs the benefits of including infinity. Lucky for us, definition 3.18 expands our previous result onto integrals of real-valued functions. We suppose that x s mu is a measure space, and that f maps this measure space onto any real number from negative to positive infinity. We do require f to be s measurable, and such that either the integral of f positive d mu or the integral of f minus d mu is finite. And of course, it's fine if they both are as well. Recall that while I've omitted the definition here, f positive is f restricted to the domain on which f is positive, and f negative is the function f restricted to the domain on which f has negative outputs. And recall that f negative makes these outputs positive so that we are working with functions similar to what we've discussed in the past. Then the integral of this entire f function with respect to the measure mu is equal to the integral of f positive minus the integral of f negative. So we return to our blue axis. However, this time, when we draw f, we don't need to worry about f being positive everywhere. So we can draw it like this. Let's take a look at f positive and f negative given this graph of f. Here I've made the positive outputs of f green and the negative outputs of f purple. Of course, it's a bit of an abuse of notation to say that this is f minus, because we need to bring it above the x-axis like this. Now we just take the integral just like we talked about before. I won't get bogged down in drawing the partitions. Just know that this is the exact same simple function approximation as we did before. However, this time, because we flipped the output sign of all of these f negative values, we actually need to subtract this red shaded region from the total integral. That way, we actually get an accurate representation of the area under the curve. With intuition built for Lebesgue integration on R, the most natural expansion is R2. However, before we can get into Lebesgue integration on R2, we need to talk about a few important definitions, the first of which will be definition 5.18, which deals with finite measure and sigma finite measure. A measure mu on a measurable space xs is called finite if the measure of x is finite. The other half of definition 5.18 is the one we'll get more mileage out of. It's the definition of a sigma finite measure. A measure mu on a measurable space xs is called sigma finite if the whole space can be written as the countable union of sets with finite measure. We can be a little bit more precise. In particular, there exists a sequence x1, x2, and so on of sets in the sigma algebra S such that X is the countable union of all these xk's and such that the measure of each xk in particular is finite. We'll return to the notion of a sigma finite measure in just a moment. However, definition 5.23 is relevant in that it secures some of the intuition that we have from Calculus 3. Definition 5.23 is about iterated integrals. We suppose that x s mu and y tau nu are measure spaces, and that f maps a coordinate pair x, y to a real number. We don't require this to be an S measurable function, just that it be a function. Then the integral of x of the integral of y, f of x, d nu of y, d mu of x, means exactly what we think it does from Calculus 3, where we evaluate the integral on the inside by temporarily fixing x, and then computing the integral on the outside. Note that I've omitted a small definition here. We previously did not specify the variable after our integrand. However, now we've got d nu of y to indicate that the inside integral is in fact y, and d mu of x to indicate that we're integrating over x. Before we proceed, we actually need to backtrack slightly to definition 5.2, the product of two sigma algebras. If we suppose that x, s, and yt are measurable spaces, then the product of s times t is defined to be the smallest sigma algebra on x times y that contains a times b, where a is a set in S and b is a set in T. The second half of definition 5.2 is the measurable rectangle. Once again, we suppose that x, s, and yt are measurable spaces. Then a measurable rectangle in S times T is a set of the form A times B, where A is in S and B is in T. These were not critical to the definitions that we've established prior to this. However, they will come up in both definition 5.25 and example 5.26. We now have everything we need to define the product of two measures, as we do in definition 5.25. We suppose that x s mu and yt nu are sigma finite measure spaces. Then for an arbitrary e in S cross t, we define the measure of e with respect to mu times nu by the integral of x of the integral of y of the characteristic function e, this time with both the input variables x and y, first in relation to d nu y, then in relation to d mu x. This definition is not necessarily intuitive. However, Axler then goes into example 5.26, which will help us visualize what's going on. Example 5.26 gives the measure of a rectangle. We suppose that x, s, mu and y, t, nu are sigma finite measure spaces. Then if A is a set from the sigma algebra S and B is a set from the sigma algebra T, then the measure of A times B with relation to mu times nu is equal, by the previous definition, to the integral of x, of the integral of y, of the characteristic function of A times B, with input variables x and y, first with relation to d nu y, then with relation to d mu x. This can be pictured to the left here. We know from definition 5.23 iterated integrals that we can handle the inside function first. To handle the inside integral, we first fix the variable x, and we integrate just with respect to y. This is consistent with what we've done earlier in the presentation, and we find that this is the measure of b with respect to nu times the characteristic function of a, this time just with the input variable x. We apply one more time our strategies from before, and we find that this is the measure of a with respect to mu times the measure of b with respect to nu, pictured here.